All skull and Gallia.
So
not that easy.
we have 20 minutes, including questions.
Okay.
So please.
Yes, I'll start. So yes, my name is James Devlin. I'm from the University of Galway, and I'm here to present today on the topic of direct flux. So I'm here to present today on the topic of direct flux via virtual faces, or as we call it, DFVF-overset, which is a method for conservative interpolation-free overset in OpenFOAM. So just a brief introduction to overset for people who aren't familiar with it. So overset uses multiple overlapping grids to discretize the spatial domain. It has quite a number of practical advantages. So it allows you to mesh quite complex geometry using very simple regular Cartesian grids. It's very good for simulation of bodies in the dynamic motion. You can fit these grids to complex bodies to capture boundary layers, etc. And there are multiple implementations of this in OpenFOAM these days, including both native functionality in ESI and FOAM-Extend. But one of the characteristics of overset is it relies on interpolation of flow quantities between the grids to enable communication between the grids. And that's true of all current implementations. This causes us some quite significant problems. So it introduces interpolation errors into the solution. It also violates the global conservation of the system. So it introduces conservation errors. It is difficulty in resolving sharp gradients such as shocks and free surfaces. So there are numerous kind of drawbacks to employing the interpolation. But it's something of a necessary evil because we need these two grids to talk to each other. Unfortunately, the grids aren't contiguous, so we have no way to calculate flux between them. If we could calculate flux between overlapping cells, we wouldn't need to use interpolation and we wouldn't have these problems. This arises because grids aren't contiguous. The overset cells have no adjoining faces, can't compute the flux. So by means of doing exactly that, what I'm going to introduce today is a general form of the finite volume method, known as the finite volume particle method. It is a mesh-free form of the finite volume method, which permits overlapping volumes. Okay, so it was developed at the University of Kaiserslautern by Dietmar Heidel. And what their aim was, they wanted to combine the advantages of mesh-free Lagrangian methods with the kind of rigorous foundation of the finite volume method. The fluid is discretized as a field of particles which represent finite volumes. So you can see it here on the right, okay? And these particles, the fluid motion is captured by two means. They move around the domain, and there's also flux between the particles. So it's an arbitrary Lagrangian scheme. The volume of each particle is distributed according to a weight function, which you can see here on the bottom is kind of norm distribution, although it doesn't have to be a norm distribution of volume within the particle. So the first thing we're going to do is we're going to normalize this weight function like so, so that it sums to 1 over at any point in the domain. And this forms what we call a partition of unity. So this means if you take any point in the domain, that the volume of all the contributing particles is summed to 1. The equations that we want to solve are of this form, the conservation equations. And if we multiply this by this test function, we get this weak form of the conservation law here. Okay. Now in this scheme, the interparticle flux is calculated like so. On the right-hand side, you can see G, Ui, Uj, which is the numerical flux function. And this beta ij here is a geometric constant, which depends on the interaction of the particle weight functions. So I won't go through it all here, but you see weight function of I and weight function of j between two particles I and j. And it's normalized by all of the particles overlapping that spot. For convenience, I break this into two half areas. So I have gamma ij and gamma ji, one belonging to each particle. It's quite an interesting scheme. It has beta is a geometric constant, depends on the particle overlap. It is units of area, so it's equivalent to intercell area in FEM. In particular, beta ij equals minus beta ji, same as the face that you would have in a mesh. And for any particle, all the sum of all the beta equals 0. And this ensures the scheme is conservative. In the special case where our particles are adjacent, this beta ij evaluates exactly to the face area between adjoining cells. So if I take test functions like so, where we just have a test function of 1, over the domain of the cell. For two overlapping cells, this looks like this, right? We have our gamma ij and gamma ji from each cell, resulting as beta ij times the flux function. If I was to move these particles so that they're adjacent to each other, this then is a standard finite volume method, and this beta evaluates exactly to the intercell area. So like I said, it's a generalized form of the finite volume method. What has this got to do with overset? So in an overset grid assembly, we have cells which are adjacent and we have cells which are overlapping, like here on the right. What I'm going to do is I'm going to employ the standard finite volume method in the majority of the grid. In the overlap region, we're going to directly calculate the flux between the overlapping cells using the FEPM. So between these overlapping cells, what I'm going to do is construct virtual faces, which have this vector area beta. And because it works at the mesh level, the solver will act on the assembled grids as if it was just a single finite volume mesh. So the solver doesn't know any different. It doesn't know that this is overset. So I've introduced these virtual faces here. Once I do that, that unfortunately has a knock-on effect on the rest of the mesh geometry. So we also need to correct the existing faces in the overlap zone using FEPM so that the sum of all the faces of each cell sums to 0. The second thing we need to do is adjust the volume. So in the overlap zone, we're going to take this volume here that is overlapped and we're going to share it between the overlapping cells. And this also means that the cell center moves to where the center of volume is of the cell. So there's some adjustment to be done to the cell properties. And we store these in an OpenFOAM dictionary. So in OpenFOAM, the process looks like this. Set up the case as normal. We run a preprocessor, which runs this geometric modification. It spits out two things. So we get a modified mesh with the virtual faces inserted, and we get a dictionary of corrected cell properties. We then run the solver as normal. And at the end, we have to put the mesh back so that we can post-process it. So this is implemented in Python. There's a couple of modifications to OpenFOAM's core libraries. But in terms of the solver, there's only one additional header file acquired in the solver. So we don't need any overset libraries, either liboverset.so or Sugar or Pegasus or any of that. We don't need specific overset solvers. We can run it with any finite volume solver. What we do need is we need Seagal, which does a lot of the heavy lifting for the geometry calculations. So our modified mesh structure looks like this. We have ordinary faces. We have faces that we've deleted here in the overlap zone. Our new virtual faces, I recalculate then these areas and the boundaries. That's the OpenFOAM mesh structure. And the same for the owner and the neighbor. Then I need to adjust the boundary patch to make sure that the patches are consistent. We insert this virtual face between overlapping cell pairs. So a virtual face looks like this. It has 2 points. And when the solver hits a face that it knows that has 2 points, it knows to calculate it according to this routine. One of these points is the face area, and the other one is the center. And I just define the owner as the cell on the overlapping grid, and the neighbor is the cell in the background grid, but it's arbitrary, really. These 2 points then are appended to the end of the point field. And we also have our corrected cell properties. So it has a list of cell indices, and for ones which need corrected, it corrects the volume and the center and throws it into these locations into the OpenFOAM mesh structure. And this is the basic kind of revised calculation routine for the faces. So just move on to some results then. All the simulations I'm going to show are on the Foam Extend 4.1. For each one, we'll have a single grid. We'll have 3 different flavors of overset, so 3 different interpolation schemes, and DFVF in purple. All the DFVF solutions are going to use the same solver as the single grid with the additional header file, and the same grids and boundary conditions as the overset cases. Overset uses corresponding overset solver, so if it's IGO-foam, it's IGO-overset foam, etc. So first case, we have a simple case of 1D diffusion with a nonlinear source term. And grid setup looks like this. So we have a boundary at 0.3 L between the background and foreground grids. And our solution looks like this. So in purple, we have the DFVF solution, and in blue is a single grid solution. And you see that they correspond pretty much exactly to the analytical solution, whereas all of the overset schemes suffer some degree of error, and also they're not continuous in the overlap zone, whereas this scheme is completely smooth. If we look at the peak temperature generated, you can see similar. So all of the overset schemes suffer from an error, whereas the DFVF scheme can follow the single grid solution almost exactly, even though it's overset. If you do a grid convergence study and we just take the L2 norm error of this field, what we'll find is that all of the overset schemes converge in the first order, okay? Whereas DFVF converges in the second order and has identical convergence behavior to the single grid scheme, okay? So all these interpolation error schemes have first order interpolation. If we eliminate this first order error, we can achieve the same second order convergence as the single grid solver. Another case, just a simple 2D lid-driven cavity. This is on quite a coarse mesh, 48 by 48 cells. Our overset assembly looks like this. So we have like a square grid placed in the center of another square grid. If we do it correctly, it should look like this. So we have a primary vortex within the overset region. And we also have a secondary and tertiary vortex formed. What we find on the coarse grid is that the existing overset schemes in foam extend don't resolve this tertiary vortex, okay, on the coarse grid, whereas it is resolved in DFVF overset. And again, we have a smooth solution field over the overset boundary. If we look at the kind of maximum of velocity, so this is the velocity across the center line, you can see that the maximum is the same as the single grid as well, whereas there's an error here for the overset. And also, if we look at the overlap zone here, it's continuous across the overlap zone, whereas there's discontinuity if we're using interpolation. Convergence properties, I just did this with simple foam because it's steady state. It's a similar story to the 1D Laplacian foam. So you can see that we're converging in the same order as the single grid simple foam. It's not quite second order in this case, but it's almost second order. So last one, I'm just going to present a simple dam break case. This is actually using the same geometry as the tutorial case in foam extend. We have an atmospheric boundary condition at the top on an initial water column here. And then we have this cylindrical bump here with a boundary fitted mesh wrapped around it. A bit more similar to how overset's used in application. I've just extended this domain upwards to prevent loss of water through the top boundary. And this is the overset setup here for the overset models. So if you do it correctly, it should look like that simple kind of dam break over a bump. First thing I'm going to look at is mass conservation. So with the DFVF, we have strict mass conservation here in purple, and the light blue is the single grid as well. Whereas all of the overset schemes suffer from a loss or gain of liquid fraction from the domain over time. So DFVF maintains strict conservation. It's inherently conservative, actually, due to its derivation from the conservation law and exact calculation of intercell areas. Free surface, this is going to get fairly chaotic because it's a fairly aggressive kind of dam break. But at least if we look at the initial kind of flow profiles or alpha equals 0.5, you can see also that we meet the profile of the single grid more closely than the overset solutions. Here you can see the overset solutions are kind of like starting to race ahead of where this wave front is. Pressure field. So this also applies to all the solution fields. So you can see with DFVF overset, we have perfectly smooth pressure field formed. Whereas with the interpolation-based schemes, there is a discontinuity between the two. We've raised that discontinuity. And then the last thing I'm going to look at is just the force on the surfaces of the domain. So this is the two snapshots of the force on the cylindrical surface. Again, the DFVF in purple and single grid in blue. And you can see that we meet it more closely than the overset. And also we don't have these kind of like spurious fluctuations in the force profile. And similar as the solution progresses, so this is at t equals 0.5, the overset's actually starting to diverge even more. If you look at the force on the right-hand wall, so on the left is just before the wave impact, so this is air pressure. You can again see that we almost completely match the single grid solution, whereas all of the overset schemes are off to a certain degree. And if you look on the right after the wave impact, you can see here is our DFVF scheme. And even though the magnitude is slightly larger, we have the same kind of impact location as the single grid scheme, whereas the overset has two different impact locations here, I presume because the wave is moving slightly faster. So yeah, in summary, an Achilles heel of overset since its inception has been this reliance on interpolation to provide integral communication. The interpolation introduces errors into the solution and breaks the conservative properties of the system. There is no need to actually employ interpolation at all. We don't need to interpolate between the grids. We can just compute the fluxes directly using the finite volume particle method. Because it's equivalent to the finite volume method, we can use any finite volume solver to do this. And it demonstrates improved accuracy over interpolation-based overset schemes, maintains strict conservation, and behaves similarly to a single unstructured contiguous grid. And this technique has been implemented and validated for both ESI OpenFOAM and Foam Extend. So yes, that's everything. Are there any questions? Yes.
Yeah, that's very legacy management in this less than the last year and great. But eventually I saw several maps still considerable.
There is for this aggressive kind of dam break case. I haven't put it in here,
Right.
but when I do a more kind of like Cartesian grid, the solution aligns much better. What I suspect is the problem here is is actually with the single grid, there's quite a lot of non-orthogonality in it. And if I could get a Cartesian background grid, that the solution would adhere better to the single grid solution. But I think for the other schemes, so say if you take this kind of velocity profile, I mean, it's a simple physical case, but the solution is still, it's almost perfectly aligned.
Right.
So
That's a good say.
yes, so this is all done with quite coarse grids. What you find with overset is sometimes to deal with the interpolation error, what they do is they brute force it with grid density. So as you decrease the grid density, you interpolate over a smaller distance, and therefore it reduces the error. That obviously has its own impact in terms of computational costs. The reason I did the this with the tutorial case that's in Foam Extend is this kind of like a nice balance. If we go any coarser than this, the overset solution will fall apart, basically. But yeah, like anything in CFD, you can brute force it with computational power if you really wanted to. Okay.
All right. I think, like in the Lagrangian character, probably you get a perfect match in the drawing data.
Mhm.
I don't know.
The
On
droplet,
average, I mean, catch everyone.
Yeah.
Yeah.
yeah. But what I want, so yeah, the free surface is very complex. What I do want to do when I'm here is I'll just do it on a Cartesian grid. And the other thing is, I didn't show it here, but in the overset, because there's no mass conservation, you also get bubbles formed in the fluid phase, which we don't have as well. So
That's good. You share this stuff.
I presume so, yes. I guess I'll talk to the organizers and share it afterwards. So this is done in Python at the moment. My current work is importing it to C++, so that then we would get the dynamic mesh functionality, and then that would make it a lot more usable to the community, I think. Yeah. So there's 3 phases, I think. The hole cutting is a bit of computational cost. The volume share is the main one, and then the base construction is very cheap. But
Sorry.
once you have the solver valid, how quickly is
Okay, so let's move on. We have 2 online presentations now. So we have first Jon Lambarri here in Spain.
Okay.
So let's talk about CFD ray tracing study, laser battery interaction, laser metal deposition with low power.
So, hello and good morning to everybody. Welcome to my talk. So my name is Jon Lambarri. I'm part of Techniker Institute. We are a research organization doing basically industrial research, applied research, and we are located in Eibar, north of Spain. So it's a great pleasure to be part of OpenFOAM conference for the first time. This is a pre-recorded talk, so I hope everything goes okay. So my topic for today is related to additive manufacturing of metals, in particular when using a laser as the energy source. So here in this slide you can see the outline for the talk. So we will start and move on to the context definition. So laser metal deposition, or LMD, also known as laser cladding, it's an additive manufacturing process, which is based on the melting of a metallic material either in powder form or in wire form. So historically this process has been used and it's still being used to repair and reinforce components, or also to mix different materials and get composition gradients. In our institute, Techniker, we have been developing laser metal deposition processes for more than 15 years. First, as a technique for repair and reinforcement of components, and nowadays we are really interested in developing the technology for 3D printing. In particular, our focus is in aeronautical materials such as nickel-based or titanium-based superalloys. These materials are quite expensive and hard to machine, so the additive manufacturing alternative makes a lot of sense. As I mentioned before, there are two different process alternatives in laser metal deposition. One is to use wire as the feedstock material, and the other one is based on powder. And this is the one that we will be dealing with today. In the powder-based method, the nozzle plays a very important role in the delivery of the material to the interaction zone with the laser. So in the market there are different alternatives, different designs based on coaxial or continuous delivery, also based on side delivery, and finally with discrete channels. In our case, we will be dealing today with a 3-channel discrete nozzle. Now we move on to the objectives of the research. Although laser metal deposition is a very promising technology, it also has some issues. Some of them are related to the big number of process parameters that must be controlled and fine-tuned in order to have a successful outcome. Porosity, lack of fusion or distortion are some of the common problems in LMD processes. In order to have a good understanding of the physical mechanisms underlying these problems, numerical methods in general and CFD methods in particular can be of great assistance. In particular, for the discrete nozzle used in PLMD, there are 3 parameters that play a role. They are the shielding gas, which helps to protect the interaction zone and to avoid oxidation, the carrying gas, which basically is in charge of delivering the powder material into the melt pool, and also the mass flow rate, which will control the addition of material into the melt pool. So, in order to have a good understanding of these parameters, we have established a series of objectives. First, we want to obtain an estimation of the nozzle operating parameters. We want to have a good idea of the powder focal position. Also, we want to check the effect of substrate and particle cloud on the laser field. Also, we want to assess the laser energy, which is lost by particles, mainly by absorption, but also by scattering. And finally, we want to obtain mass, energy, and momentum sources to further model the LMD process. We now move on to the description of the modeling workflow. LMD is quite a complex process in terms of physics. There are a lot of things going on. So it is common practice to divide it into different blocks, depending on what's the focus of your research. So it's normally divided into 3 blocks. The first block deals with laser irradiation and material addition. The second block deals with melt pool generation, and the final block deals with solidification in order to predict microstructure, residual stresses, and also sometimes the surface roughness. In our case, we will be dealing with the first block. That is, we are interested in obtaining as outputs the laser power, which is attenuated by the powder cloud, also the distribution of the powder, and the increase of temperature in the powder. In this slide, we show our modeling workflow. We have divided the research into three, let's call it, sub-models, each one corresponding to a row in this sketch. So, in the first sub-model, we deal with the nozzle, and we consider the powder cloud in Lagrangian formulation. For this step, we need as inputs the nozzle geometry, the shielding gas and the carrying gas flow rates, the powder mass flow rates, and also some parameters related to the particle cloud, such as the radius distribution and some physical magnitudes. For this step, we use OpenFOAM in reacting partial foam solver, and we turn radiation off. And as outputs, we get the particle positions, the Lagrangian particle positions. In the second submodel, we do some ray tracing calculations. This is outside of OpenFOAM, but we use particle positions as inputs and also experimental characterization of our laser source, which is basically the laser power and the efficiency of the optical system, the laser caustic, that is the three-dimensional distribution of our laser irradiance, and also the substrate position. We get, through the use of CMAX software, the effective laser field, which is then mapped back into OpenFOAM in the third submodel. Let's say in the last row, we repeat again the first Eulerian Lagrangian model as in the first submodel, but in this case, we turn radiation term on for the Lagrangian cloud. So we get as outputs particle positions and particle temperatures. In the following slides, we will discuss in some detail the different submodels. So, submodel number 1 deals with the Eulerian Lagrangian description of our gases and particle clouds. So, for this step, the flow of a transient, compressible, and turbulent argon-air mixture is considered. We consider a mixture because normally argon gas is used both for the shielding and for the carrying gas. Regarding turbulence, we decided on k omega SST with wall-insensitive wall functions. You have a sketch here of the domain, which contains both internal and external flow. So regarding inlets, we have one for the shielding gas, which is located over here, and 3 discrete inlets for the carrying gas and the powder cloud. So we also have an interaction zone of fluid nature, which is densed more densely to have a better description of the interaction afterwards. We also consider the presence of a substrate, and everything is inside an enclosure. Boundary conditions, we consider shielding gas volumetric flow rates between 15 and 50 liters per minute. The carrying gas is fixed at 3 liters per minute, and the powder mass flow rate is between 3 and 24 grams per minute. So at t equals 0, we have our domain, that is both the internal nozzle and the external part, completely filled with air. Then we inject argon gas at the inlets, and we let the model run until both the nozzle and the interaction zone are filled with argon gas. At this point, we inject our Lagrangian cloud under the following assumptions. A two-way coupling is considered. The particles represent Inconel 718 material, which is a nickel-based superalloy widely used in aeronautical applications with this 250 microns in diameter. So the particles are injected at the powder inlets using patch flow rate injection model. Also, the particle diameters follow a Rossum-Ramler distribution, which is experimentally calibrated using scanning electron microscope images. As active forces, we consider gravity, drag, and virtual mass. We also include hard sphere collision model for the particle-wall interactions, with the detail that we also create a patch in the substrate wall so that some particles can escape, and in this way we somehow simulate or estimate what would be the powder catchment in the real process. So we then extract the particle positions for time steps, which will be used in the next submodel, which is the ray tracing one. So the second submodel deals with ray tracing interactions. This is done in order to study the way that the laser interact with the powder cloud and the substrate. I won't go much into detail because this is not related to OpenFOAM, but basically the way it works is that we have a spatial discretization of our laser source, which is based on a very detailed experimental characterization, and we divide our laser source in approximately 1 million rays. These rays are launched from inside the nozzle, and they can scatter and also be absorbed and reflected by both the particles and the substrate. When a reflection event happens, each ray is subdivided into 100 child rays, which are traced on until they reach a detector or they are lost. So since we don't have information on the roughness of the particles and the substrate, we consider a Lambertian scattering. And we locate a different number of virtual sensors to capture the effective irradiance at different positions in the interaction volume. I hope this will be more clear in the next slide. So this is just a quick slide to try to illustrate my previous points. So in the ray tracing software, we import the cut geometry, and we have a laser source inside the nozzle. Here the rays will diverge from the nozzle and will move towards the substrate. In case they hit by chance a particle, they will scatter and subdivide in 100 child rays, as I mentioned before. So in this interaction zone, we have located a certain number of virtual detectors which can trace the energy that goes through them, both in one direction or in both directions. So in this way, we can keep track of the reflected energy, which is interesting for the next submodel. In the final submodel, we again repeat the Eulerian-Lagrangian calculation in a similar way as in the first submodel, with the exception that in this case we consider the energy term for the Lagrangian particles. So the effective laser field that we have calculated using the ray tracing software is imported into OpenFOAM and is modeled as the G field for the P1 radiation model with a super Gaussian distribution, which is nothing more than a Gaussian distribution with an exponent that is different than 2. Here we make a small modification to the intermediate library so that the particle properties can be input as a function of temperature. As a side note, if you are interested, we have a collaboration with the University of the Basque Country where we can measure the emissivity, technically the total hemispherical emissivity as a function of temperature, which is quite interesting for these kind of problems. So once we have imported our laser field back into OpenFOAM, it looks like this in a cross section. So you can see that the laser is more intense, is actually focused inside the nozzle, and then it diverges towards the substrate. Let's see now what kind of practical information can be extracted from all these models. One aspect that is really important in LMD is to have a good protection of your interaction zone, since really high temperatures can be reached, and this could lead to oxidation and therefore degradation of your mechanical performance. So what we see in these two cross sections is that the interaction zone is well covered even when we use a lower volumetric flow rate for the shielding gas. And we can also see what we could consider to be Kelvin-Helmholtz instabilities due to the shear velocity here between the argon gas and the atmosphere. Another very important point in LMD is to have a good coincidence of your laser working position and your powder focal position in order to maximize the process efficiency in terms of powder catching. So here you can see on the right hand side a picture of our actual nozzle, and we see that the powder converges more or less at 12 to 13 millimeters from the nozzle tip. So to see if this checks with the model, we have extracted the void fraction of the Lagrangian cloud, and we have extracted some profiles that I will show you in the next slide. In this slide, we see a profile of the void fraction created by the Lagrangian cloud. So on the left-hand side, we see the cross-section, and we can check that the void fraction is quite small, so the two-way coupling approximation seems reasonable. On the right-hand side, we can see a fit of the particle volume fraction as a function of the distance from the nozzle. So if we try to fit it more or less to a Gaussian shape, we find that our focal position is close to 13 millimeters, which is in good agreement with the nominal distance provided by the manufacturer and also by the pictures that we showed you before. We now show some results from the ray tracing submodel. So in this step, the most interesting output for us is to have the effective laser irradiance at the substrate and also in the interaction volume. So as an example, I'm showing here the results from two virtual detectors, one for a case with a low mass flow rate of 3 grams per minute and one with a high mass flow rate of 24 grams per minute. So as you can see, the particles cast like tiny shadow and steal some energy from the laser. So for higher mass flow rates, the effect is more intense than for lower mass flow rates. Another interesting result for us is to notice that the power losses are almost linear with the powder mass flow rate. To get this result, we have normalized the laser charge power to 1 watt, and we have measured the total, we have integrated the laser irradiance at the working distance. In this case, we recover the total power loss, and we see that it's pretty much linear with the powder mass flow rate. I think I am running out of virtual time, so I will try to go quickly through the last slides. So submodel 3, the last submodel, gives us some interesting statistics about particles. In this case, we have filtered the particles that are below the nozzle tip and over the substrate surface. And we can check the effect, for example, of increasing the shielding gas flow rate from 15 to 50 liters per minute. And we see an increase in the peak velocity from 4 to 5 meters per second up to 10 meters per second. Similarly, for temperature, we can extract histograms of temperature in the interaction zone. And we see that the inclusion of the reflection effect has a dramatic effect on the temperature distribution. So finally, we move to the conclusions and future work. So to sum up, we have developed a combined CFD and ray tracing model, which allows us to have a good idea of what is going on in a PLMD process in terms of gas dynamics and laser matter interactions. So practically, we have seen that a gas flow rate of 15 liters per minute is enough to provide a good coverage of the interaction zone. We have also checked that the powder focal position is located at approximately 30 millimeters from the nozzle outlet, in agreement with the supplier manual. We have also seen that the shielding gas flow rate does not have a big effect on the powder focal position. Also, that laser power losses are very closely linear with the injected mass flow rate. And also that the reflection from the substrate has a great effect on particle temperature. So it must be considered when dealing with this problem. So future work, we are developing a PIV, particle image velocimetry experiment to try to validate the particle velocities. We also want to check the effect of different laser power. And finally, and most interestingly for us, we want to use the Lagrangian cloud as sources for further modeling of the LMD process. In particular, we want to study the melt pool and the track creation. Finally, we would like to acknowledge the support of the Basque government in the development of this research, in particular through the Elkartek program. So this is all from my side today. It's been a pleasure. Unfortunately, I won't be able to attend the live session, so if you have any question, please drop it via the platform or using my email. So thank you very much and hope to see you around in the next conference.
Yeah. Can you see my presentation now?
No, just a second.
No, maybe.
Yes,
Okay. Yes.
perfect. The stage is yours, Silvio.
Yes, just a second. Okay, yeah. Thanks for having me, and I'm going to talk about our cloud microphysics Euler-Lagrange library in OpenFOAM. And my name is Silvio Schmalfuß, and I'm working at the Leibniz Institute for Tropospheric Research in Leipzig, Germany. But let's start with an introduction. I think you're all aware of climate change, and recently it got a lot of increasing media attention. And one of the main issues is the global surface warming, which you can see in the graph here at the right-hand side. And currently we are approaching the 1.5 degree centigrade above the pre-industrial levels for the global surface temperature. And most of this is due to the radiative budget changes. And most of these changes can be attributed to this graph. All the things in this upper box here are anthropogenic sources, and only the solar radiance is of natural source. And within these contributions, almost all are very well. One exception, and this is the total aerosol effect, which is split up into two different effects. One's the direct effect, which means that aerosol in the atmosphere can directly absorb or reflect radiation. And then we have the cloud albedo effect, which means that clouds are formed from aerosol, and then depending on the cloud type, contribute to either surface cooling or surface warming. And yeah, these two effects have the largest uncertainty, as you can see here in this column. And to reduce this uncertainty, there are numerous activities in field lab and numerical studies. And we at Tropos have an instrument called LASES-T for investigating the interactions of turbulence, aerosol, and cloud microphysics. LASES-T is short for Turbulent Leipzig Aerosol Cloud Interaction Simulator. It's a wind tunnel, and you can see a sketch here on the right-hand side. It spans over 4 stories in our laboratory, and you can see a human model for the scale here next to the measurement section. The flow inside this wind tunnel goes clockwise here in this graph. And it has 2 different branches. Each has up to 6,000 liters per minute flow rate. And we can precisely define the thermodynamic and flow conditions within these 2 flow branches, and we can control it separately. The velocity inside the measurement chamber can be up to 1.5 meters per second, and we can precisely control temperature and dew point temperature between -40 and +25 degrees centigrade. Additionally, we have an active turbulence grid to introduce defined turbulence to the flow, and we can inject well-defined size-selective particles between the 2 branches so that we can then do experiments with turbulently mixed air masses and aerosol. Well, I'm going to shortly present what instrumentation we have there. We have, for example, for humidity, we have two dew point mirrors. For temperature measurements, we have several PD100s and a constant voltage anemometer. We can measure the velocity with rain anemometers, a laser Doppler anemometer, and for constant temperature anemometer, and with the particle counter or with a dot-phase Doppler anemometer. This has the drawback that we can only do point measurements. Additionally, we have no information on particle history of the aerosol particles we added. The fluctuations. And this is where CFD simulations come into play. And this is an exemplary experiment we are doing, so we can have. So now we are seeing a cross section of the measurement section. On the left-hand side, we have, for example, low humidity. At the right-hand side, we have higher humidity. And then we inject particles which behave according to their surrounding. And with the simulations, we can, for example, get the particle size distribution. You can see at the top right. This we can also get from the measurements, but what we, for example, cannot get from measurements is something like this humidity distributions on the bottom right-hand side. So this is why we need CFD simulations. And we did this with this Euler-Lagrange library I'm going to talk about. So now you know why we need this. And in the next slides, I'm going to talk about how we do this and what we are doing with it. So the current version is based on the OpenFOAM Dev version from 2020. It makes use of the built-in Lagrange library and is based on the well-known kinematic cloud class. Here we use some code from the thermal cloud class, and some models, especially for the injection, had to be adapted. And we implemented some specific models for the cloud microphysics. And I'm going to talk about these three models. The first is deliquescence and efflorescence model. Then we have a droplet growth model, and then we implemented heterogeneous squeezing models. At first, for deliquescence and efflorescence effects, what is it? Hygroscopic materials can absorb moisture from their environment even when the relative humidity is below 100%. You can see it depicted here on this graph and the pictures on the right-hand side. And water-soluble hygroscopic materials can absorb enough water to go into a solution at a certain relative humidity. For example, here at the right-hand side is for sodium chloride. If you inject twice sodium chloride particles into an environment with a certain relative humidity and then increase it, at some point the particles absorb enough humidity so that they have a sudden increase in their diameter. So then they suddenly go into solution and jump to a higher diameter, which is here at around 75%. So you can see it here with these open circle symbols. And then after they went into solution, they go to their equilibrium diameter, depending on the relative humidity. This change from solid to liquid phase is called deliquescence. And there's also a reverse process for this. The crystallization from the liquid phase to the solid phase is called efflorescence. It can be that these two phase changes have a large distance with respect to their relative humidity. For example, the efflorescence relative humidity for sodium chloride is something like 50%, and the deliquescence relative humidity is 75%. So these processes might occur at these different humidities, and this causes a hysteresis effect, and then you have this hysteresis loop here. We modeled this with simple if conditions like this. At first, we check if the particle is in which phase state the particle is in. If it's solid and the relative humidity is above this deliquescence humidity, it changes its phase state, takes up water from the surrounding and releases heat. If the particle is liquid and the relative humidity is below the efflorescence humidity, it changes the phase state to solid, releases all water to the surrounding, and takes up heat. And every other case, it does nothing. And there is simulation for this. This is what we already have seen in the introduction. So here we have two different airflows coming from the top. At left airstream, we have a relative humidity of 60%, but the right one, we have 85%, so that we are on average on 72.5% relative humidity. And then we inject sodium chloride particles with a wide diameter of 370 nanometers. Relative humidity of 75%. So on average, we are below this deliquescence humidity. And in measurements, we would use, for example, this Willis optical particle counter to measure at a certain distance from the aerosol injection point to get the particle size distribution. And this can then look like this graph here on the bottom left. So we have some white particles left. You can see here the left peak. These are the 370 nanometer particles. And then we have deliquesced particles with a white peak here. And these account for approximately 70% at this certain height we measured or got the data from. And now with the simulation, we can, for example, see that at this point, we only have 30% of the relative humidity values above this deliquescence humidity, so that we can see that there's a large influence of turbulence on deliquescing these particles. The next model, it obeys a growth law where the mass change rate is proportional to a diameter, and the difference in and surface difference between the ambient saturation with respect to water to the surface saturation of the particle. And the calculation for the surface saturation takes into account the Euler theory. The Euler theory then is again a combination of the Raoult effect and the Kelvin effect. The Raoult effect says that depending on the amount of solute that went into solution in the droplet, creates a depression of the surface surface saturation ratio, which you can see here in this red curve, and the Kelvin effect, which accounts for the curvature of droplets, which says that depending on the surface curvature of the droplet, you get an increase in surface supersaturation via droplets interface. So according to this, we can calculate the mass change rate, and then we can have mass exchange with the water vapor field. And of course, if water is evaporated or condensed, we have to calculate also the heat exchange due to latent heat release. This time I'm going to show an exemplary simulation with another cloud simulation chamber called PyChamber, which is a Rayleigh-Bernard cloud chamber at the Michigan Technological University. You can see a sketch here. So it has a square cross section of 2 meters times 2 meters. It's 1 meter high. The bottom surface is warmed, the top surface is cooled, and both of these surfaces are saturated with respect to water so that we can form a Rayleigh-Bernard cell inside. An aerosol is injected and we can study the growth of droplets in there. Here in this picture, you can see the swirls that are created due to this Rayleigh-Bernard convection, and additionally diameter. And with our library, we can then, for example, have a look at aerosol and droplet statistics, like, for example, from top to bottom, the liquid water content, the number concentration of droplets and aerosol, and the removal rate of droplets and aerosols. And we can then, for example, have a look at the influence of different aerosol injection rates. And we can also here, this is two-way coupled, so we can also see the influence of the droplets on the temperature, or for example, on the humidity. So the next model is the freezing of droplets. Currently, we only consider immersion freezing. That means for droplets to freeze, we need a particle inside the droplets that acts as an INP, an isonucleating particle. And we implemented three different models for this. One is called a singular model, which is from colleague Heike Wex. And there each particle has a fixed freezing temperature, which is assigned at the injection of the particle. And we have two stochastic models by other colleagues of mine, Susan Hartmann and Dennis Niedermeyer. There the freezing probability for each particle accumulates at each time step. And this accumulated freezing probability is then compared to a randomly drawn number. And if the freezing probability is higher than this number, the particle freezes. And this freezing probability depends on the number of these INPs and some stochastic properties. You can see the behavior of these models here at the right-hand side. At the bottom, you see the temperature in degrees centigrade. And at the y-axis, you can see the ice fraction at the different temperatures. And you see the solid lines are for 800 nanometer particles, and the dashed dot lines are for 500 nanometer particles, which shows that, for example, smaller particles have less INPs and freeze at lower temperatures. For these models, we had to add a lot of additional properties to the particle class, for example, freezing temperature for the singular model, the number of INPs, the contact angles, and stuff like this. And we had to also modify the injection models. And I want to show you also exemplary simulation for this, for the freezing of differently sized particles inside our wind tunnel lasers team. This time we have two different flow temperatures of -4 and -20 degrees centigrade. And we inject particles of different sizes, namely 500 and 800 nanometers. And these particles contain SNOMEX as INPs. The SNOMEX is a commercially available isonucleating particle, which consists of bacteria or algae called Pseudomonas syringae, and they have a protein which is then the isonucleating particle. And you see a result here. At the left-hand side, you see particles with a dry diameter of 500 nanometer and the right-hand side of 800 nanometer. And they are injected from the top. In black, the particles are unfrozen, and the bluish part here, the larger particles are more likely to contain IMPs, and they are more likely to freeze, which is in accordance with the diagrams I just showed. And what we can also see that we have frozen particles in warm region and unfrozen particles in strong turbulent mixing. With this, I want to end with a summary and an outlook. We've seen that CFD simulations are helpful in understanding the phenomena that occur inside LaserST and also other cloud simulation chambers. And OpenFOAM is a perfect tool for this because of its versatility. We implemented several models for cloud microphysical simulations. Those were telecrescence and efflorescence model. We implemented the growth law, taking into account the Euler theory, and we implemented immersion freezing models. And as an outlook, I'm currently porting all this stuff to OpenFOAM 10, and I'm thinking about directly porting it to OpenFOAM 11, which is on the horizon. I want to improve the current models. For example, I have to include the latent tweet release for freezing models. And I want to implement further models like ice growth and collision coalescence. Okay, that's it. Here are the sources I mentioned, and I want to thank you very much for your attention.
Thank you, Silvio, for your very nice presentation. Do we have any questions? Yes.
I see you can hear me.
Not that good.
Hi, Silvio. Thank you for your talk. I was wondering, maybe I missed it. You did wind tunnel measurements and your simulations.
Yes.
And did you show a comparison of those both?
Not yet, but I have some backup slides.
Oh, okay. Yeah, that's nice.
Just have to find them. Yes. Yeah, here's one. I have to share the screen again. So here's an exemplary comparison between simulation and experiment at the right-hand side. For example, for this telecrescence measurements, you can see the particle size distribution in red for the simulation, and then blue for the experiments, and I think they fit quite well.
Maybe another one. Can you make a comment on the influence on turbulence on the particle growth?
Yes, it really depends on the experimental settings. For example, if we have really high differences in temperature, relative humidity, we see strong influences. Like this, we see here at the same slide. At the position where we measured, we only have 30% of the values the particle have seen with relative humidity is above the telecrescence humidity. So if everything would have been on would have been like laminar, so the particles always see the same, so to say, air parcel, there should only be 30% of the parcels telecrest, but here we have 70% of the particles already telecrest. So there's a large influence of turbulence, I think.
Thank you. Thanks. Any other questions? So maybe I can ask a few things. So this microphysics library, will it be available for sharing, or is it something that you still need to develop? Or
at the moment, it's a bit messy, to be honest. But as soon as I'm done porting it to the newer OpenFOAM versions, I'm thinking about releasing it as a GitHub repository or something.
Oh, okay.
But if someone is interested, I can, of course, always share my code with interested people.
And we have another question here.
Just a little bit of technical question. I noticed that you're using OpenFOAM 10. Is that the simulation you were using as using OpenFOAM 10 or?
What was the question again? Sorry, I didn't get you.
Because I saw you do have a parafoam display of the particles in one of the slides. For some reason, I have OpenFOAM 10 and I compile everything. I couldn't display the particle. For some reason in the parafoam, there's no cloud, kinematic cloud display there. You have no way to display it. I don't know if you encounter the same problem or you have some tricks to make it work.
I'm aware of there were some differences between very old OpenFOAM versions and newer OpenFOAM versions, but I don't know if this is still the case in OpenFOAM 10. But there, sometimes there was an option like use old OpenFOAM particle stuff or use newer one. And I think also some older ParaView versions are not compatible with the newer ones, but I'm not really sure about this at the moment.
My trick on that is I did the same. So I save this as a BTK file and then you can import it.
I did that too.
I made
I
it
couldn't
work.
open.
Oh, okay. I made it work. Anyway,